So in today's video, we would see how to perform cluster analysis in R. While doing cluster analysis in R, we shall first compute the distance matrix. For distance matrix computation, we would define a toy data set on 6 fishes and the nutritional component of those 6 fishes and then calculate the distance object. After computing the distance object, we shall see how to perform a hierarchical clustering. So, to perform a hierarchical clustering, we shall be using the inbuilt dataset in R called state.x77. However, the state.x77 is a dataset on the 50 states of USA. To make our life easier and to make or to understand the components of cluster analysis, we shall be taking the first 10 rows of the data set. Using the first 10 rows of the data set, we shall perform the hierarchical clustering. Once the hierarchical clustering is performed, we shall see how to plot a dendrogram out of it and make meaningful inferences from the dendrogram. So, the learning objective of this video is threefold. The first is how to make a distance object in R. The second is using the distance object how to calculate a hierarchical cluster, and finally using a hierarchical cluster object how to plot a dendrogram. So, we shall be first demonstrating how to compute distance or dissimilarity matrix in R. While doing that, we shall be working on a data set called the fish data set. The fish data set has 6 fishes and the nutritional content of the 6 fishes in terms of their energy, fat and calcium measurement. So, I can run this piece of code. So, just this is nothing but this a vector of fish names, energy, fat and calcium values, and use a data.frame command to create the data set and run data 1, and we get the data set. So, here is our data set. We have the fish name, 6 fishes, their energy, fat, calcium. Now, while doing our distance matrix computation, we only need these 3 columns, energy, fat and calcium. So, what we do is we would be creating another data set. This time we would be calling it as data 2 with energy, fat and calciums, and rename those rename the rows as the name of the fishes. For example, if I run first, let me run the command. When I run the command, this is what we get. So, this is energy, fat and calcium values of mackerel. So, MC stands for mackerel, PR stands for perch, SL stands for salmon, SD for sardine, TN for tuna and SH for shrimp. Obviously, the first question is how do we visualize this data? Note that this is not a normal 2-dimensional data. This is a 3-dimensional data. And to visualize a 3-dimensional data in R, we need to have scatterplot 3D in the R library. Now, scatterplot 3D is a package which needs to be installed, and that can be installed using install.packages scatterplot 3D. Since this library is already installed in this machine, I would just call the library by using the code library scatterplot 3D, because this would load the library. Then I would create a template. So, let me first create the template of the plot, and when I run this, this is what I get. If I zoom it, this is the blank plot. So, here are my 3 axes, fat, energy and calcium, and somewhere here would be the 6 fishes. So, let me just close this and let me just run this. Let me put the fish names with their labels so that it's easy to identify where each fish stands, and when I zoom this is what I get. Okay, so here is my shrimp, here is my sardine, here is my mackerel, here is my tuna, here is perch, and here is salmon. And how did we do it? So on the blank frame, what we did is we used the text command, and the position of the text was specified by their position, by their energy, fat and calcium content position, right? So the X, Y, Z positions automatically. Now let's just zoom it once again. The question of importance is, if I ask how much is sardine similar to salmon, or tuna similar to mackerel, or perch similar to sardine. In fact, how much is each of the fish similar to one another? Had this been two-dimensional, I could have easily obtained what's the two-dimensional distance between the fish based on the two dimensions. But note that this is three-dimensional, and in more general multivariate problems, we expect this to be n-dimensional. So the problem reduces to how do we find the distance between this. Now we all know we can find it using Manhattan distance, or using Manhattan or the city block distance, or using the extending the Euclidean distance from 2 dimension to 3 dimension. So there are various ways of finding distance, the more general Minkowski distance, and all of them can be implemented in R. The main workhorse to compute the distance function in R is the dist command. So what this does is it takes the object or the data frame whose distance we need to compute, and it has a method argument. Now the default method argument is the Euclidean distance, but if we need to specify some other type of distance, for example Manhattan or the city block 1, then we can specify method equal to Manhattan. So what it gives is, it produces something called a distance or a dissimilarity matrix, which we shall be calling as a distance object also. So if we run this, so what we are doing here is, for data 2 we are computing the distance by the Manhattan method. So, and we are storing it in DST. So once we run this and then type in DST here to see what it is, we see that this is the distance matrix, and we have mackerel, we have perch, we have salmon, we have sardine, we have tuna, and here you see a mackerel is missing here, but from here we have perch, salmon, sardine, tuna and shrimps, and we have their values. Although the look of the object is matrix like, note that this is not a pure matrix, because here shrimp is missing and here mackerel is missing. So what we can do is we can convert it into a matrix. So the function is data dot matrix of the distance object, and we are restoring it in again another object called DST. So here the first DST here is the distance object, and here DST is the matrix object, converted the distance object using data dot matrix. And now if we run this and type in DST here, so we just type in DST, we get the matrix. This looks like pure matrix object with the diagonal elements to be 0. That is sensible, because the distance between mackerel and mackerel should always be 0, and the lower triangle is equal to the upper triangle. So that's the symmetric matrix, meaning the distance between mackerel and perch is equal to the distance between perch and mackerel. The advantage of converting a distance object to a matrix object is that we can now plot this using the image function, and if we do that, this is what we get. So what we have done is we have given values to each square. So now these values, this 27 means it's a distance between sardine and mackerel. This 46 means the distance between perch and sardine. This 48 is distance between tuna and sardine. So we see that the fish perch is most similar to tuna, while sardine is most, no sorry, while yes, so while sardine is most dissimilar to tuna in terms of nutritional content, and this calculation has been done based on city block or Manhattan distance. We can similarly produce the same plot using something called the Euclidean distance. So I can just use dist data 2 and don't give the method argument because by default the method is Euclidean, or specify method equal to Euclidean so that we are in sync with the previous command, and then run exactly the same set of commands but now replacing dst by dst1, and when we run this we get another image plot. The moment we zoom it, you see this is what you get. So the values have changed. Note that the redder is the value the closer the fishes are. For example, here it's 4.1 and the value between salmon. So mackerel is closest to salmon and mackerel is furthest to sardine. So what we see here is that the further the fishes are, the whiter is the color, the closer the fishes are, the redder is the color. So we conventionally call this as a heat map image. We would be now demonstrating hierarchical clustering using an inbuilt data set called state.x77. Now state.x77 is our data which is inbuilt in R. It contains 50 rows which corresponds to 50 states of USA and 8 columns which correspond to the population, income, illiteracy, life expectancy, murder rate, high school graduation percentage, mean number of days with frosting and total area of these 50 states. For sake of simplicity and understanding, we would take the first 10 states and explore how to do cluster analysis on it. So if we run this, we create an object called state.x77 underscore 10, and state.x77 underscore 10 contains the details or the data of the first 10 states. So it starts with Alabama, then Alaska, Arizona, and we have up to Georgia. Now the main workhorse for computing hierarchical clustering is H-classed. Now H-classed is a function which takes the distance matrix as its input and not the data frame. So what we can do is we can create the distance matrix using the dist function. So if we just use dist state.x77 underscore 10, it produces the Euclidean distance. If we specify the method equal to Manhattan, then the dist function of state.x77 underscore 10 produces the Manhattan distance. What we do is we create both the distance and store in two objects, namely dist1 and dist2. So if we want to see what is dist1 and what is dist2, so this is dist1. Dist1 is the Euclidean distance. So for example, between Arizona and Alaska, the distance is 453022.303, and this is the Euclidean distance. And for Arizona and Alaska, the Manhattan distance is 456797.64. So now after getting the two distance function, what we can do is we can just pass that on to the H-classed function. So pass the distance object to H-classed function. If we don't specify any method, the default method is complete linkage. If we want average linkage, then we should specify method, and here it would be method equal to within quotes AVE or average in full. Similarly, if we want single linkage, we should say method is equal to within quotes single. So specifying the methods make the algorithm take either average linkage or single linkage. If we don't specify the method, the default is complete linkage. So what we do here is we perform hierarchical clustering of this state.x77 using a complete average and single linkage, but here the distance matrix has been computed using the Euclidean norm, and we store it in 3 objects called HC1, HC2, HC3. So it runs fine. So HC1 is the hierarchical clustering of state.x77 underscore 10, where the distance has been computed using Euclidean method and the clustering has been computed using the complete linkage algorithm. Similarly, we can perform the same or replicate the same analysis on the Manhattan distance. So just replace dist1 by dist2, remaining is same, and the objects from HC1 to HC3 now changes to HC4 to HC6. So these are basically objects in which we stored them, and now we run it. So now we have basically 6 objects: HC1, HC2, HC3, HC4, HC5 and HC6. Each of the 6 objects corresponds to one way of distance computation and one way of clustering. So we can plot it. What we can do is we can divide our plotting window into 6 zones or 6 elements in a matrix format with 2 rows and 3 columns. So this is what the parmfrow command does. So just run this and it's been done. Now we plot each of the 6 objects and with a heading that the method of distance computation and the method of clustering. So if we run this, what we get is a page. So just if I zoom this, yes, so here is my 6 dendrograms, and here you see this is the dendrogram obtained using a Euclidean distance with complete linkage. This is a dendrogram obtained using Euclidean linkage, a Euclidean distance and average linkage. This is Manhattan distance and single linkage. So there are a few points to note here. The first point is that plot of a clustering object automatically produces a dendrogram. So R is intelligent enough. When you say plot of a clustering object, it knows that it has to produce a dendrogram and it produces a dendrogram. Now of these 6 dendrograms, so all of them are on the same data. What is different? The method of distance computation and the method of clustering. But all of them are giving very similar results. So what we are seeing here is that Alaska is completely different from the other states. That's number 1. Finally, what we are getting for most of the states, we have the combination. There are few states which are keeping together. For example, California, Arizona and Colorado are keeping together for most of the times, except for here where Euclidean and single linkage, where California, Connecticut and Delaware comes in. Arizona and Colorado goes here. But for most of the times, the cluster composition is remaining the same. The cluster positions might vary according to the value it gets, but the cluster composition is same. For example, here if it's Connecticut, Delaware, here is also Connecticut, Delaware. The position of Connecticut and Delaware has changed. So here it's in the middle and here it's in this side. Now this is because different algorithms lead to different values, but the final interpretation still remains the same. So what we conclude is that we can get a different dendrogram based on the method of selection of distance computation and the algorithm of hierarchical clustering. But whatever way we take, all of the methods should lead to more or less the same interpretation. To conclude today's session, let us recapitulate what we have learned. We have learned the workflow of creating hierarchical clustering in R. So to create the hierarchical clustering in R, we have first learned how to use the dist function. Then we have learned how to use the hclust function. And then finally, how to use the plot function of an hclust object to get a dendrogram out of it. Thank you.